Okay, complex circuit number 3, the third one on that sheet linked on the agenda. This is again, the third one. It is similar to the first one. It just has a little bit more complicated second section. So current would leave the battery pack here, flow through a resistor, now split 3 ways. So we have 3 branches here all in parallel with each other, and then we come back together, go through a third one, and back to the battery pack. So step 1 down on our chart here is finding total resistance. So total resistance. Again, thinking with different rules of series and parallel, we sort of have 3 things in series with each other. So what you want to do is simplify, this area here down to its equivalent resistance. So if we could figure out, this whole section in here, what is its resistance equivalent, and then just sort of add them up in series then. So parallel, so we need our parallel method. 1 over what we're looking for is 1 over 5 plus 1 over 7 plus 1 over 9. Now, I definitely don't feel like finding a common denominator, so I'm just going to go with the calculator version. I'm going to go with 5x to the negative 1 plus 7x to the negative 1 plus 9x to the negative 1. Get my answer x to the negative 1, to flip it over, and 2.2. So resistance of this section, 2.2 ohms. And then we go for resistance, equivalent for the entire circuit here. So it is just going to be a 3 plus a 2.2 plus a 3. So what is that? 6, 7, 8, 8.2 ohms for the entire circuit. So let's keep track of that. So we've got resistance total or equivalent. I kind of flip-flop with that. Sorry. For the whole circuit here is 8.2 ohms. Let's figure out the current next that leaves the battery. So what is it? 8.2. Putting it down in the chart here. 8.2 ohms. Current that leaves the battery. It'd be nice to get a current total. Sometimes we say. So current that leaves the battery, it would flow this way. The total going through this one, but then splitting 3 ways here, flowing through each branch, coming back together, and then all of it flowing through here and back to the battery. So let's do an Ohm's law with that real quick. So V equals IR. So voltage 30 equals current I, looking for that total resistance 8.2. Divide that over 30 divided by 8.2, 3.6. We'll go 3.66 rounded. Amps, of course, current flow. So I've got total resistance for the circuit, total current for the circuit. Let's start figuring some stuff out. We know that the total 3.66 leaves the battery and flows through the 3 ohm resistor, splits. We could figure that out in a moment, but then comes back together. So we do know the current through this resistor and this resistor. The way I labeled them in the chart this time is I'm calling this one number 1, number 2, number 3, number 4, and then finally number 5. So we know the current moving through 1 and 5. Let's put that in the chart. Current through 1, that's a 3 ohm resistor. That's going to get full current. So 3.66, again, because it's just the only thing in the circuit. So when it leaves the battery, all of it has to go through that first one. It will split up the current 3 ways, adding up to that total, and then come back together, but go through here. So we do know the current through what we're calling resistor 5, the 3 ohm at the bottom there. And that is the full current, 3.66 amps. The current's going to split. This 3.66 is going to split 3 ways. Most of it going down this way because it's the easiest branch, 5. The least amount going down this way, but it will split that 3.66. It will split not evenly because we have different resistant branches here, but that'll add up. So when we do get, these 3 values here for the other currents, it'll add up to hopefully 3.66. Give or take some rounding. So what do we know then? Next up, let's find the voltage drops, because now something else to remember is things in series have different voltage drops. So it'd be easy to find it here with Ohm's law, V equals IR, and then pretty easy to just see what's left, and that would be the voltage drop for all 3. Things in parallel all get the same voltage drop, and then we'll be able to solve for the I's going down each branch. I don't know if this is becoming any easier or more clear, but hopefully it is. Let's see. So voltage. So voltage drops. Let's do that. Let me get rid of some of this stuff here. Oh, no, smearing. All right. Fix that later. So let's find voltage drop here. So delta V is what we know 3.66 through a 3 ohm resistor. And I'll just set it up for down here. It's going to be the same calculation. So delta V, 3.66 times 3. And let's figure out what that voltage drop is. Let's see, 3.66 times 3. 10.98. Let's go ahead and call that 11. So 11 volts, and that'll be the same number, 11 volts. And that allows us to figure out what the voltage drop is for this section here. Maybe we'll fill in the chart so far. So we got 11 volts and 11 volts. That takes place at 1. So 11 volts, and that also is the drop, we call it, down at the last element. And then whatever's left of the battery, each one of these will have that same drop because things in parallel have the same potential difference drop. So 11 and 11, 22, it was 30 volts to begin with. So 22 of them get used up with a little rounding, get used up at these two elements. So what is left for this whole section? So this whole section then enjoys a drop of what's left, 8 volts. Everything here gets the same 8 volts. So then we just do an Ohm's law, V equals IR, and we find the I going down each branch. So all of these are going to get an 8 voltage drop. And that's why you can't just tally the voltage column and get the voltage of the battery. It just often won't work. It would be a coincidence if that worked. The column that works best is the power column at the end, and then you do an IV for the whole circuit, I for the whole circuit, V of the whole circuit, and you can check that. Sorry, I got off topic. Let's get back over here. Let's find the I. What I goes this way, what I current goes this way, and what current goes that way. So we just have to do a bunch of little V equal IRs. So V, everybody gets the same voltage drop. So 8 equals what I down the 5 branch. 8 volts equals what I down the 7 branch. 8 volts equals what I down the 9 branch. So we got to figure out these currents. So 8 divided by 5. So 1.6 amps flows down this branch. 8 divided by 7. 1.14 volts, amps goes down this center branch. And the last one there, 8 divided by, well, that's a 9. 0.89 goes down the final branch. And these are amps of current. And again, if we add these up, hopefully with rounding, we would get the 3.66 there. And we're just about done. Down the 5 branch, we did have the most amount of flow number-wise. The most amount of current did go down the easier branch, something to take note of. So 1.6 down that branch, 1.14 down that branch, and 0.89 down that branch. And that should add up to, I guess I should take the time to check, 1.6 plus 1.14 plus 0.89, give or take some rounding. I get 3.63, 3.66. I can live with losing 0.03 to rounding. Anyway, so we can do the final check to make sure that we did everything correct. Let's just tally the columns over. Forgive me for calculating. I've got 11 times 3.66. I get 40.3, 40.3. 8 times 1.6, I get 12.8. 8 times 1.14, and I get 9.12, 9.12. And 8 times 0.89 is 7.12. Should probably just make a nice little Excel sheet for this that would tally everything according to my own calculations. That would be lovely. Any Excel people out there will know what I'm talking about. 3.66. And the last one, did I just do that right? All right, 40.3. Let's tally it up, see if it worked. So if I tally this column here, it should be equal to an IV for the entire thing. So power for the entire circuit, I, 3.66 times the 30 volts. Let's just see what that works out to be. 3.66 times 30 volts is, I'm getting 109.8 watts of power. And let me tally up this power column here. 40.3 plus 12.8 plus 9.12 plus 7.12 plus 40.3 is 109.64. All right, I can live with that also. All right, looks like we did it right. Later.